Hey everyone, so these are the video solutions to Worksheet 6.5. We're going to be talking about applications of exponential and logarithmic functions in here. The first problem, number one, this is a fairly straightforward compounded interest problem. We're told that we're investing $500 into an account that bears interest at 0.75% compounded monthly. So for part A, we're basically asked to come up with a formula for the amount that's a function of time in years. Now the fact that we have this interest compounded monthly tells us that we're going to use a specific form. So we've got two different formulas for compounded interest. Interest that's compounded given a discrete number of times within a year versus continuously compounded interest. So in this case, since it's compounded monthly, it's compounded 12 times each year. So we've got the discrete form. So our formula is going to look like this in general. We'll have A is equal to P, which is our principal, times 1 plus R, which is our interest rate, divided by N, which is the number of times we compound the interest per year, times N to the power of T, where T is the number of years. Now what we'd like to do here is come up with a function for this amount where T is the only unknown left. So we'd like to have A as a function of T. Well, let's go up to our givens here and see what we can figure out. Well, the initial investment is our principal. So this $500, that's going to be our P. The fact that it's compounded monthly tells us N, the number of times that we're going to compound this in a year. So N equals 12. Excuse me. And now this is where we look for our interest rate. Now, our interest rate is always going to be expressed as a decimal form, as a percent. Now, if you think about 0.75%, that's 0.75 per 100. So that's 0.75 divided by 100, or 0.0075. This is what we're going to use as our R. So we always need to convert that percentage into a value. So we've got our P, we've got our R, we've got our N. T is going to be left unknown, so we're ready to go with our function. So we've got 500 as our P times 1 plus our interest rate of 0.0075 divided by N, which is 12. And that's raised to the power of 12 times T. So here we have a function that's ready to go. All we need to do is plug in a year, and it'll tell us the amount in our account, which we are going to do right now. So for part B, we're asked to determine how much is in the account after 5 years. So essentially, T is equal to 5, and we'll use the formula that we just came up with in part A. So we're going to find A of 5. So that's going to be 500 times 1 plus 0.0075 divided by 12 raised to the power of 12 times T. In this case, it's 5. So our calculation is going to end up being 500 times 1 plus 0.0075 divided by 12 raised to the power of 60. Now, probably the most common mistakes that are made here are with the syntax in your calculator, so you want to make sure you do this carefully. The way that I kind of like to do it is I'll first calculate this value. So I'll say 0.0075 divided by 12, enter, and it'll give me an answer. Then I'll just hit plus 1. So it'll take answer plus 1. That'll give me the value inside the parentheses. Then I'll hit raised to the power of 60. So it'll give me this answer. So say like ANS or whatever the answer abbreviation is, raised to the power of 60. That'll give me this whole number. And then I'll take all of this and just say times 500, and it'll multiply that whole thing by 500. That's the way that I like to do it, rather than typing out a whole string of things and having to be careful for parentheses, but whatever works for you is great. Either way, when we type this into our calculator, you should get an approximate value of 519.099. Now, I'm just going to go ahead and truncate this after 3 decimal places. Normally you'd be told to round, probably like round to the nearest cent, and rounding is always rounding up. There's no rounding down. You either round or you truncate. If you're asked to round, we would definitely take this to $519.10. Although if the bank's a little stingy, they don't want to give you partial cents, they may just go ahead and truncate it right after 2 decimal places and just give you 519.09. I know I would if I was the bank, because you haven't quite earned all the way up to 519 and 10 cents. But just be careful for that. The directions aren't specific of what to do in this case, but if we did round to the nearest cent, this would be our solution. Okay, so for part C, it's kind of the same thing, except we're asked to determine the account after 10 years. So this would be t equals 10. So we calculate a of 10, and that would be 500 times 1 plus 0.0075 raised to the power of 12 times 12, raised to the power of 12 times 10. So we'd have 500, 1 plus 0.0075 divided by 12, raised to the power of 120. Again, we want to be careful with typing this into our calculator, making sure that we get an answer that makes sense. So this should be more than 419, but not $1 million or anything. We should end up with 538.929. Again, if we're going to round to the nearest cent, we would end up with 538.93. So $538.93 if we round. And just for fun, let's do this again. So we're going to round. We're going to determine how much we've got in our account after 30 years. So t equals 30. So a of 30, we're going to have 500 times 1 plus 0.0075 raised to the power of 12 divided by 12. I keep saying that wrong. And we're going to raise this to the power of 12 times 30. Now this, if we type this into our calculator, we should get 626.117, which if we round to the nearest cent, we would get 626 and 12 cents. Okay, so that's just us using this function to calculate the amount of money in our account. Now for part E, we're asked to determine how long it'll take for the initial investment to double, round answer to the nearest year. So if we're asking how long will this take, we're going to be looking for t. So we know that we're going to want to set up an equation where we can solve for time t. And we want our investment to double. So we started off with 500, so we're going to want it to double to 1,000. So let's go ahead and set this up now. So if we're looking for t, we'll have our equation, which is 500 times 1 plus 0.0075 divided by 12 raised to the power of 12 times t, because t is unknown at this point. But we want that initial investment of 500 to double to $1,000. So now we just have to solve this equation for t, and we'll use our strategies for solving exponential equations that we discussed in section 6.3 to do this. First, let's go ahead and divide both sides by 500. If we do that, we're going to get 2 is equal to 1 plus 0.0075 divided by 12 raised to the power of 12 times t. If this had been triple, we would have expected to be a 3 here. If we wanted to see if something was going to, multiply by a factor of 10, we would have ended up with a 10 over there. But now we need to go ahead and keep solving for t. So we want to get that t, which is in the exponent slot, out of there and down out in front. And the way we do this with exponential equations, we've isolated our exponential. We've got a constant on the other side. We're going to go ahead and we're going to take the ln of both sides. And we'll proceed from there. Power of 12t. Now, using properties of logs, we can take that exponent and move it down. So we've got the ln of 2 is equal to 12 times t times the ln of 1 plus 0.0075 divided by 12. Now we want to isolate t, so let's go ahead and divide I'm going to want to divide by 12. That'll get rid of the 12. And we'll go ahead and we'll divide by the ln of 1 plus 0.0075 divided by 12. Because those two numbers will reduce down to 1. And if we divide both sides, that is plus 0.0075 divided by 12. And then I'll just leave us with t. So we'll go ahead and we'll bring this up here. So we're going to get the ln of 2 divided by 12 times the ln of 1 plus 0.0075 divided by 12 is equal to t. I know it kind of seems obnoxious to have to carry through all these ln's and everything, but if you start rounding within the problem, you're going to leave yourself open for compounding rounding errors throughout your problem. So it's best just to sort of leave the ln's and the logs in your calculation, and in the very end, then you can do all the rounding that you need to do. So if we go ahead and calculate this, so t is going to be approximately 92.448. Now think about what this is saying. So we hit 92 years, and we go a little bit further, and then we'll hit the $1,000. So if we're asked, well, how long will it take to actually get to $1,000 with we're rounding to the nearest year, saying 92 wouldn't make sense, because after 92 years, we haven't gotten to 1,000. It wouldn't be until the 93rd year that we had crossed the threshold into doubling our investment. So it makes sense to round this to t equals 93 years in this case. Okay, so now we're going to move on to number 2. So we've got the temperature in Fahrenheit of a roast beast t minutes after it's removed by the oven from the oven is given by this formula right here. So first we're asked to find and interpret t of 0. Well, this is easy. We just plug in 0 for t and we see what we get. So again, that would be the time is equal to 0 minutes, just for context. So t of 0 would be 70 plus 100 times e to the negative 0.01 t, which in this case would just be 0. So we're going to get 70 plus 100 times e to the 0, which is just 1. So that's going to give us 70 plus 100, which would be 170 degrees Fahrenheit. That would be our temperature. So the way that we would interpret this is we could say that when the beast is removed from the oven, so that's time 0. So at time 0, we're taking it right out of the oven. So it's as hot as it's going to be. When the beast is removed from the oven, it has a temperature of 170 degrees Fahrenheit. Now we could expect that as we leave this outside, it's going to start to cool down. So in part B, it asks us, well, when is the temperature of the roast beast cooler than 80 degrees Fahrenheit? So it's not asking when is it equal to 80 degrees Fahrenheit, but when is it cooler then? So when is the temperature dropped below 80 degrees Fahrenheit? So essentially it's asking us for what time or for what t is our temperature function less than 80. And that's how we're going to interpret this. And essentially we've got an inequality here that we have to solve for. So we take our temperature function, which is 70 plus 100e to the negative 0.01 t, and we're going to set it less than 80. And now we just go through and we solve this inequality. So I'll subtract 70 from both sides, and I'll get 100e to the negative 0.01 t is less than 10. I'll divide both sides by 100, and I'll get go ahead and do that. So I'll get e to the negative 0.01t is less than, and that's just going to give me 0.1. So now we solve this inequality. And we can look to section 6.3, where we talked about exponential inequalities. And if we think about what we do next for this, the first thing we want to do is we want to get it to 0. So we've got e to the negative 0.01t minus 0.1 is less than 0. Then we're going to want to find the zeros. So this is this procedure we talked about in 6.3. So we've got e to the negative 0.01t minus 0.1 is equal to 0. We're going to solve this through. So we have e to the negative 0.01t is equal to 0.1. We take the ln of both sides. So we've got the ln of e to the negative 0.01t is equal to the ln of 0.1. And that's going to, on this side, we've got the ln of e, so they're going to undo each other. We've got negative 0.01t is equal to the ln of 0.1, which gives us t is equal to the ln of 0.1. We divide both sides by negative 0.01, and we would get approximately 230.3. So what this tells us is that somewhere after 230 minutes, the temperature of our roast beast has dropped below this. And we could, if we needed to, we could set up a sign diagram to do this. So we know that we're starting at t equals 0, and we've got our 230. This is kind of overkill at this point, but it's good to consider. We could pick a point like 1, and we could pick a point like 500, and we know that this is a 0 of our inequality. And we could go through and we could test, and we'd figure out that it would be less than, it would be positive on this interval, be negative on this by testing points. I'll spare you the gory details. And this would be our solution interval. So we could sum it up by saying that after 230.3 minutes, the beast drops below 80 degrees Fahrenheit. And that would be a perfectly reasonable solution there. Okay, so for part C, we need to sketch our graph here. So let's go ahead and we'll build this. So again, we know that our function here, t of t, is 70 plus 100 e to the negative 0.01t. So if we think about what's going on here, just to kind of understand the graph, we've got e to a negative power, so we know we have exponential decay with a coefficient of 100. So if we were to start building a curve here, I'm going to start with just y is equal to 100 e to the negative 0.01t. Now this is going to be exponential decay, and we know that it's going to have a horizontal asymptote on the x-axis. We also know that it's going to have an initial value or y-intercept at 100. So when t is equal to 0, we're going to have a y-intercept of 100. Now to go from this to our function for t, we are basically adding 70. That's a vertical shift of 70 units. So to sketch a graph of t, we're just going to want to take what we have here and shift it up 70. So here's t. If we shift everything up 70, we're also going to shift this horizontal asymptote up to to 70 that we're going to have, and that y-intercept is going to go from 100 up to 170. And we're going to have a curve that looks like this. So this is our function t of t. So this is our curve. We've got an initial temperature of 170. We've got this horizontal asymptote at 70 because of the way that we've shifted it. And in part D, we're asked to interpret the horizontal asymptote. Well, let's think about it. As T increases, the temperature is decreasing to 70, but it never quite gets there. We could think of this as the room temperature. So the temperature of the surrounding environment is 70 degrees, so something left out in the environment is going to slowly cool down to it, but not drop below it. You know, if anything, the room temperature might, you know, come up even a little smidge because of the environment is warming up by the increased temperature of the object in the room. But anyway, regardless, we'd go ahead and we'd say that for this one, that the room temperature is 70 degrees Fahrenheit. So that's how we would interpret this horizontal asymptote of 70. Okay, so that does it for 6.5, and I will see you all in the next video.